Okay, hi, welcome everyone to Protocol Labs Research Seminar Series. Really glad to have you all here, and welcome to those watching the recording as well. I'm glad you took the time to see what we're doing here in Protocol Labs Research Seminars. If you want to be informed of future seminars or just stay up to speed on what we're doing at Protocol Research more generally, you can visit the research website. It's research.protocol.ai. And just drop your email address in the footer to sign up for announcements or quarterly newsletters. You can find a playlist of our previous seminars on the outreach page of our website, and just go down to the bottom. It's under public talks. You'll also find other ways to connect with what we're doing, including a link to current opportunities through our RFP program. Today's speaker is Bernardo David. Bernardo is an associate professor at the IT University of Copenhagen, and also a member of the Center for Information Security and Trust. From 2017-2018, he was an assistant professor at the Tokyo Institute of Technology. He holds a PhD in computer science from Aarhus University. Bernardo, welcome. I'll let you take it from here.
Thanks for the introduction. So as you can see, today's topic is actually the combination of two papers. I'll be talking about our recent results, TARDIS and CRAFT, which together yield better randomness beacons, and MPC with financial penalties from time lock puzzles with universally composable security. It's joint work with Carsten Baum, Jesper Buslis, and Sabine Oechsner from Aarhus University, and with Raphael Dosley from Monash University. Our agenda today will be a short introduction to the problem of defining time lock puzzles in a composable way, and then I'll go through our contributions that show more or less how we can do that and the applications, then go through our notion of abstract composable time, heading on to our construction of UC secure, publicly verifiable time lock puzzles, and finally to the applications to general purpose multi-party computation with output independent abort and efficiently unbiasable randomness beacons that we can construct from these publicly verifiable TLPs. And I'll finish with some pointers to interesting future work that's coming up in a more short or longer term. So to begin with, let's talk about time lock puzzles. They basically allow you to encrypt a message to the future in the sense that you can create a time lock puzzle containing some message that can only be retrieved after some time is elapsed. During this time elapsing, you can do a number of steps to try to solve this time lock puzzle, after which you can retrieve the message that was contained in there. In order to construct these primitives and to model their security, we need a notion of a sequential computational task that can be shown to last at least for a number of sequential steps in order to be solved. So we need to model this notion of sequential computation that cannot be parallelized or have its efficiency increased by higher computational power. We need to be able to show this idea of sequential computational steps that we can pile on top of each other in order to ensure that enough time is elapsed between a time lock puzzle being published and between its solution. The first people to define and introduce a notion and construction of time lock puzzles were Rivas, Shamir, and Wagner in '96, who introduced both the notion of time lock puzzle and a construction based on the hardness of this iterated squaring or sequential squaring of elements of groups with unknown order. The idea here is that they conjecture and they make this assumption, which seems to hold still today, that if you generate a group of primitive residues modulo n, where n is a RSA modulus generated from primes P and Q, the same way you would generate an RSA public key crypto system public key, you cannot quickly compute for a random element G from this group, G to the 2 to the T. So you cannot quickly do that. This will take at least t sequential squarings. This is basically the assumption. And if we think of it in more details, it would tell you that even if you have higher computer power than other parties doing this computation, it will not help you parallelize this computational task in order to compute g to the 2 to the t faster than computing these individual sequential squarings. These days, we know that actually you can get some speed up if you have more computational power, but it still looks like a very reasonable assumption. It stands for a reasonable amount of time now. And we can use that to build a time lock puzzle following the RSW construction. The idea is basically that you take the message that you want to close inside the puzzle, and you compute your puzzle as both a random element from the group, a random element G, and the message times that random element G to the small t, where small t is equal to 2 to the big T, number of steps you want of squaring, modulus phi of n. Basically, knowing phi of n allows you to compute these several squarings with just one exponentiation steps, because you can see that phi of n here is the order of the group, and knowing the order of the group, you can already compute the exponent you will raise your random group element to in order to get to the final computational state. And then if you want to solve it, you basically solve it by computing big T sequential squarings so that you can obtain, again, G to the small t, and you get the inverse of that. You multiply the inverse of that by the message times G to the small t, and you obtain your message again. This very nice and elegant construction has been around for many years, and recently there has been some renewed interest in this, since it has been realized by the community, specifically this paper by Veselovsky in last year's Eurocrypt, that you can use this assumption to also build verifiable delay functions and other interesting time-based cryptographic primitives. However, we have a number of problems in this field of time-based cryptographic primitives with the slow release of information and so on, which first of all begin with the lack of composability. This means that we cannot really use these time lock puzzles as building blocks, as generic building blocks in more complex protocols, without having to reprove the security of the whole protocol, including the security of the time lock puzzle used in that construction. So we need some notion of composability in order to do that. And we would usually like to work in this universal composability framework that's highly accepted as a good notion for cryptographic protocols composability. But then we run into another problem. What is time in this framework? This framework does not consider the existence of time, really. It's a completely asynchronous framework where you have events that happen and you don't really have a notion of elapsed time. There exists some models of time in the UC framework, but as we'll see, they don't really help us. We have an even third problem here. Even if we have a notion of time, how would we enforce sequential computation? The problem we run into is basically the following. In the UC framework, we have this all-powerful environment that is running several experiments in many multiple sessions, because we want to talk about generic composability, meaning running a protocol in multiple parallel sessions concurrently with many versions, many instances of other protocols and instances of itself. And when we do that and we try to prove security, we have this environment that needs to distinguish between an ideal world execution of the protocol in each session from a real world execution of that protocol. Now, even if we have some notion of time and we can talk about time elapsed between one event happening and the next event happening, we run into the following problem. Let's say I give the environment a time lock puzzle like the one we just constructed before, Now this environment can use these multiple sessions that it's working on as multiple separate oracles to solve this time lock puzzle in one single instant in time. So let's say we have all of the sessions, session 1, 2, until session big T, being executed in one instant in time. What your environment can do in the UC framework is that it can send to the first session G and receive G squared. Then to the second session, it sends G squared and receives G to the fourth. And then it keeps doing that until it reaches session T, at which point it can send G to the 2 to the T minus 1 and receive as answer G to the 2 to the T, which it can use to retrieve the message from the time lock puzzle. So essentially, we need to find a way to both model time in UC and to model this notion of sequential computation meaningfully so that we can describe, model, construct, and prove time-based primitives such as time lock puzzles. And then using the fact that they are universally composable, try to use them as black box building blocks in more complex protocols. Our contributions towards this are the following. First, we present a model for abstract time in the UC framework, where we are not caring about wall clock time or synchronization or anything like that. We just model elapsed time in a completely abstract way without relation to the physical world, but having enough structure that we are still able to reason about the order with which events happen and the time elapsed between these events and the relative delays between these events. Using this abstract model of time, we introduced the first UC treatment of publicly verifiable time lock puzzles. They are publicly verifiable in the sense that a person who solves such a time lock puzzle can efficiently prove to any other third party that a given solution has been obtained, while requiring that third party to compute just for a constant number of steps independent from the difficulty of the time lock puzzle, independent from the number of steps you had to compute in order to solve the time lock puzzle. Moreover, we show that in order to construct such time lock puzzles, even without public verifiability in the UC framework, you need programmable random oracles. You cannot escape the need for a programmable random oracle. However, we can still, fortunately, instantiate our construction from the so-called global random oracle model, which makes a lot of sense for real-world applications where you would replace this one global random oracle model with a actual hash function following the random oracle heuristic. But we do show that we cannot avoid random oracle programmability if we want to do this with UC security. Using this primitive, now we build this new notion of multi-party computation, which we call multi-party computation with independent abort. The novelty here is that we can build this against a dishonest majority, meaning that all parties but one are corrupted by an adversary, in such a way that the adversary can, in the end of the protocol, learn the input and cause an abort, the output, I mean, not the input, and cause an abort, and while keeping the other parties, the honest parties, from learning this output. However, the adversary must make a decision to cause this abort before it knows the output. In all of the other MPC protocols that we have now with dishonest majority, the adversary can learn the output before it makes the decision to cause the abort. So you can make a very rational decision here about whether you want the protocol to abort or not. With our new notion, the adversary is really tossing a coin when it's making his decision. This, in particular, implies that we can obtain fair coin tossing, even with a dishonest majority, which is something that is impossible to obtain in the plain model. But still, we would need our full-blown general MPC framework to do that. So we also show that we can build efficient, guaranteed output delivery coin tossing, which gives us unbiasable randomness beacons without going through all the overhead of doing general purpose MPC. As I'm going to show you in the end, there's a very, very simple protocol that we can use for obtaining an unbiasable randomness beacon. So let's start going through how we build all of these different contributions on top of each other to obtain our final applications. But before that, I'd like to talk a little bit about the related words that are there now. First of all, as I said before, there are notions of time for the UC model that basically model wall clocks. They are functionalities that allow the parties and the simulator and environment and function and other functionalities to obtain the current time, basically. So any party calling this functionality can ask for the current number of elapsed time steps or something like that. In our case, we do not expose elapsed time. As I'm going to show you, we just have a way to inform the functionalities, but not the parties, unless they invest computational work that the time has elapsed, without telling them how much time has elapsed since their last activation or how much time has elapsed since some event in the past. So we have a completely abstract notion of time that only makes sure that you know that time has elapsed, but you don't know how much. There were, as I said before, a number of standalone malleable time lock puzzles and VDFs based on iterated squaring. And very recently, actually a couple of days ago and 5 days ago, there were two related works that were posted on the ePrint archive by Katz and others, and by Ephraim and others, where they construct non-malleable time lock puzzles that are not composable, but still achieve no malleability in the sense that an adversary cannot maul several time lock puzzles together to obtain a new time lock puzzle containing a message correlated to the messages in those mauled time lock puzzles. This notion is actually trivially implied by our UC security guarantees. But the interesting thing in these related works is that because they don't achieve our composability guarantees that are stronger, they can also construct time lock puzzles with weaker assumptions, meaning that they don't need a programmable random oracle as it is needed for UC security. So they can build that in the algebraic group model and using only a observable random oracle. Also, it's interesting to notice that while the work of Katz and others is based on iterated squaring, the work of Ephraim and others builds on standard time lock puzzles and VDFs and compiles those generic primitives that are not non-malleable into non-malleable counterparts. In the topic of trying to obtain output independent abort and some sort of fairness for secure computation, there has been work doing that for the case of two-party computation using standard non-composable time lock puzzles. However, this work obviously does not offer composability guarantees, so you cannot run these protocols in parallel with others, and it's restricted to two parties, whereas we can obtain similar guarantees for multiple parties in dishonest majority. The first step in our modeling and in our work is to eliminate the need for this global clock and substitute it by a global ticker. This global ticker can be accessed by other functionalities, by honest parties, and by the simulator, the ideal adversary, throughout the execution, but it will only respond to functionalities when asked if a new tick has happened. A tick means that a new instant in time has elapsed, but the global ticker will only tell functionalities and parties, not parties, only functionalities that this happened upon being queried. And it will not tell the functionality how many ticks have elapsed since this last query, it will just say whether there was a new tick or not. On the other hand, the parties will only obtain some information that might indicate that time has elapsed from the functionalities when some event happens. For example, when they receive the output of a time lock puzzle from a time lock functionality, or when they receive a message through a communication channel with delay. In those cases, they will know that time has elapsed because some delay has occurred, some ticks have occurred, but they never get any message from the global ticker telling them that. Actually, the only thing they do with the global ticker is activate the global ticker with an acknowledgement every time they believe that they have executed all the computation they should execute at some point of the protocol. And upon sending this acknowledgement to the global ticker, they don't get any message back. So they never get any feedback from the global ticker that allows them to infer how much time has elapsed, or even if time has elapsed at all. They only observe the outputs from functionalities. This basically means that the parties are oblivious to any time information. They don't get, by default, in our framework, any information about the lapsing of time. They only get information that certain events are happening in certain orders. This allows us to do a very nice abstract modeling for protocols where the actual time elapsed between different events does not matter at all, but where we care about the order with which these events happen. This makes it much easier for us to write and prove these protocols because we don't have to keep worrying about keeping track of time elapsed between events and between the view of the adversary and the parties of this global clock modeling wall clock time. All we have to do here is to make sure that the order of the events happens in the right time, in the right order with the right relative delays. And our global ticker will allow the functionalities to keep some track of that without leaking time. Of course, we could construct a functionality that always queries the global ticker, asking if new ticks have happened, keeps an internal counter of that, and then tells to the parties how many new ticks have happened since the last time they activated this functionality with a query. You could do that if you want to build a global clock, but you do not have to do that in order to use our framework. As we will see for the case of time lock puzzles and our output independent abort MPC and randomness beacons, we really don't need to care about concrete time at all. And then you might be wondering, why do the parties tick the global ticker? The short answer is that in order to make all the composability guarantees hold nicely and to make proofs go through, we need to make sure that all of the parties, the honest parties, are activated every time there is a tick. They don't need to know there was a tick. They don't need to know how much time was elapsed since any past event, but they need to be activated at least once every tick. They could be activated 1,000,000 times, it wouldn't make any difference, but they need to be activated at least once. If we don't do this by requiring the parties to activate the global ticker with an acknowledgement, we would need to restrict the class of environments we work with. Now, we need to use this model to model our time lock puzzles. So we're going to start talking about time lock puzzles in terms of ticks instead of physical time. So we generate a time lock puzzle that will be opened after a certain number of ticks. And in this time lock puzzle notion, we don't care about the exact physical time meaning of this number of ticks. We only know that we have this number of ticks. And when we use this in conjunction with other protocols, with communication channels and other time primitives, what we do is that we know, for example, the communication delay of a given channel and in terms of ticks, and we know the time lock puzzle delay in terms of ticks. So we can make statements like a message is received through this channel before the time lock puzzle is solved. And very interestingly, we can work in the so-called semi-synchronous model as well, because we don't really need to know the exact delays. We just need to know, in some cases, for example, the randomness beacon case, we just need to know that we have a finite delay in our communication channel, and that we can adjust the time lock puzzle delay to be larger than that finite delay, exactly because it is finite. Now, we have this notion of ticks very nicely. Now we can argue about our time lock puzzles taking longer to be opened than a message to be delivered and things like that. However, this still doesn't help us solve the problem I had told you before, where the environment can try to brute force a time lock puzzle using several parallel sessions. In order to get around that, we need a better modeling of this iterated squaring assumption in the UC framework. We do that by capturing this assumption into a generic group model style functionality that allows parties to do operations, squaring operations, or just simple multiplications over these group elements, but never receiving an actual group element or a representation of a group element. They only receive a generic string that is a handle for that group element, so that they can say something like, you square the element that is identified by this string and give me the corresponding identification string for the resulting element. What we do in this functionality is that parties can ask for multiple squarings per tick, but they only get the handle for the result of this squarings in the next tick. So we ensure that they can only do the next squaring step after the next tick happens and they receive the result. This is also a global functionality, meaning that the simulator cannot explore any superpower over this functionality in our security proofs. This functionality is external to the actual simulation and the environment distinguishing this simulation from a real world execution. No one can touch it. No one knows what's in its internal states. And this models the fact that the sequential computation should be hard for everyone, both the honest parties and the adversary, and also the environment, of course. Our functionality looks a little bit like this. It starts with this basic interfaces here. Let's say we are at tick number I after the execution started, and that we already have an internal list in our functionality containing, between brackets here, the random string representing a given group element and the actual group element that this string corresponds to. Using its interfaces, any party can do the following: request a new random group element, which will make the functionality sample this group element randomly from our group, and return to this party immediately the random string that identifies this group that is now also stored in the internal table. It has a squaring interface that allows a party to ask the functionality to square the group element identified by a given handle. And when this interface is activated, the functionality actually computes the squaring, stores the squaring in its internal table if the resulting group element is already not stored there, generates a new random handle, stores it in the table, but it does not tell this new handle to the party. It just says that the squaring has been completed. And it has a get results interface that allows the parties to receive the handles for all of the group elements that were already stored and assigned to their random handles in the internal table before the current tick. In this case, it was elements G1 to GK. Now, let's say we did what we did in this figure and ask for a squaring of element G identified by G in brackets random string. In the next tick I plus 1, we can actually get the results of this squaring and receive the handle for our results, which would enable us to now ask for the squaring of this result and get the next step of the sequential computation. So this is basically the interface that we have to deal with the iterated squaring assumption by Rivas and others. We also have the notion of a special owner party who receives a trapdoor that allows it to compute any number of squarings instantly. This trapdoor would basically be the P and Q that we use to generate the modulus n for the group of primitive residues, modulo n. And the way this works is basically that we actually have a create interface in this functionality that allows only the owner to initialize the functionality and obtain this trapdoor. However, later on, if I give this trapdoor to another party, they can use it to immediately obtain the result of a squaring on a new random element or any other element that was already registered in the functionality, or any number of squarings, not only one, but they can obtain all of these operations immediately. This will be extremely important for the public verifiability that we will give to our TLP construction. Now, to the actual publicly verifiable TLP construction, before I describe the algorithms, I will say that each owner will use a new instance of the FRSW functionality that embodies the iterated squaring assumption for each new time lock puzzle it generates. And I will denote two instances of global random oracles by H1 and H2. Remember that when we say that when we have a global random oracle, we work with the same random oracle in all sessions, it doesn't mean that we can only have one instance of the global random oracle. We can have as many instances as we want, but it means that we must use the same instances in all of the executions of the protocol. We don't generate a new instance for each execution for each session. So let's see how our time lock puzzle construction works. The creation starts by having the RSW group created inside the FRSW construction functionality, which gives the owner the trapdoor. Now the owner gets a random element G in step 2. In step 3, the owner computes G to the 2 to the T, where T is the number of computation steps or ticks, using the trapdoor. Remember that the trapdoor allows the owner to compute this instantly. Now the owner will compute what we'll call tags. First, by computing the first random oracle, global random oracle, on the concatenation of the first element G, and then the G to the 2 to the T, our last element that we obtain after the T squarings. Then it will compute H2, that's squaring the second random oracle on the concatenation of the H1 it computed before, the trapdoor that it obtained from FRSW, and the message that it is trying to lock into the time lock puzzle. Finally, it will generate the tags as tag 1 equal to this value H1 XOR message concatenated with a trapdoor, and tag 2 is basically the H2. And our final time lock puzzle will be the starting group element G, or rather its random string that is its handle, and the 2 tags. Notice that this means that our time lock puzzle is at least as large as our message. This is necessary in the UC framework because we will be required in the proof of security to extract this message M upon looking at a time lock puzzle. And this can only be done if the time lock puzzle is as large as the message, so it can contain information about the whole message. Now, after we have this, let's see why we do this funny H1 and H2 when we solve the time lock puzzle. They will basically allow us to make sure that the time lock puzzle was not tampered with. In order to solve it, we compute the G to the 2 to the T sequentially by doing T squarings. From that, we will be able to recompute our H1, right, by calling the first global random oracle on G concatenated with G to the 2 to the T. And using that, we can retrieve from tag number 1 the message concatenated with the trapdoor. Then we can also check that our tag number 2 is equal to querying the second random oracle on H1, trapdoor, and message. And finally, we'll make sure that this whole time lock puzzle is actually generated using this specific trapdoor to compute G to the 2 to the T from G. If all of these checks check out, we know that the time lock puzzle was valid and that we have successfully solved it. And we can output M and TD as, the trapdoor, as both the output of the message inside the trapdoor and the proof that we have actually solved the time lock puzzle. Now, from this, it's actually quite simple for us to obtain public verifiability. Basically, if I give you a solution and a proof, M and trapdoor, to a given time lock puzzle, in order to verify this, all you need to do is to parse the time lock puzzle, obtain G, then use my trapdoor that I gave you as the proof that I solved it to obtain G to the 2 to the T, and then you use G to the 2 to the T, the trapdoor I gave you, the message I gave you, in order to repeat all of the steps, the checks in steps 2 and 3 from the solve procedure, which will make sure that what I'm giving you is a valid solution to this time lock puzzle. So at any point, any party can join the execution of a protocol and check without the help of any other party that a given solution plus proof of a time lock puzzle is correct. So especially in our randomness beacon application, if we're using a public ledger, a public bulletin board, or a broadcast channel to broadcast this time lock puzzles and later broadcast solutions, I can prove to a new party who's joining the execution, who wants to check that a previous random value is correctly obtained, I can prove to them that a given value was obtained from the time lock puzzle without requiring them to do all the work to solve this time lock puzzles. Now, let's see what we can do with this. The very interesting thing we can do with this is basically obtaining this notion of output independent abort. That's basically poor man's fairness. We know that we cannot hope to get fairness against a dishonest majority. And even with other set of assumptions, that would be impossible. So what we can do, the next best thing that it seems that we can do is our new notion of output independent abort, where the adversary can still force the protocol to abort, and it can still learn the message, the output of this protocol, while keeping the honest parties from learning the output. However, the adversary cannot see what output would be obtained before it chooses to abort. And most importantly, it cannot bias this output because it simply doesn't know what it's going to be. So it doesn't know whether it's sending of the next message or it's aborting of the protocol will bias the output in any way because it simply doesn't know what the output would be before time lock puzzle is open. And I want to show you just a general idea of how we can do it. We need a lot of MPC machinery to actually do this in the general case. And we also need very, very careful modeling of communication channels and broadcast channels with delay and so on. But I want to give you a general overview of more or less how this would look like. Let's say we have the doctor here computing against the master and his companion, and they would exchange messages, right? And what we want to do is that the last message, we want to put it inside a time lock puzzle. Usually, the master here, the adversary, would be able to see what this last message was from the doctor and the companion, and then she would be able to judge whether she wants to send her last message or not in order to cause the protocol to abort or not. However, when we put all of the last protocol messages inside time lock puzzles, the adversary, in order to not cause an abort, it must send its own time lock puzzle before the honest time lock puzzles are opened. However, she needs to do that Well, before the time lock puzzles are open. So she cannot see what the last message from the honest parties are, and she cannot know what the output that would be obtained in case she sent her last message would be. So she needs to make this decision without any rational strategy based on the output. She's now completely confused, and she cannot use the actual output to decide whether to abort or not. The applications for that are better MPC with financial incentives, because now when you try to do the game theoretical analysis of what the punishment to an aborting adversary should be, your life is much easier, because the adversary cannot make any rational choice based on the actual output that would be obtained. The adversary will be basically flipping a coin. And talking about flipping a coin, this will give us fair coin tossing and randomness beacons. As I told you, in order to do this in general for MPC, we need a lot of more complicated machinery and overhead in doing general purpose MPC, especially in the case that we want public verifiability, because we actually build this with public verifiability and with financial punishments to aborting adversaries. But if we just want to do the very simple randomness beacon, we can do something much, much, much simpler and more efficient. We can build a Randall style beacon that, differently from Randall, can be proven to be unbiasable even against aborting adversaries and adversaries who are rich enough to pay for the punishments that they will receive. If you're not familiar with Randall, that's fine. I'm going to show you how this works more or less now. But if you are, I guess you know that in Randall, you punish adversaries who abort so that you have to pay to introduce bias. But here, the adversary can never introduce bias. And this is how we do it, informally. All parties first will broadcast a time lock puzzle containing some randomness to be solved in a number T of ticks in a way that we know that T is larger than the broadcast delay. After waiting for the broadcast delay, remember that our parties do not have any notion of time. They cannot time the broadcast delay. So in order to do that, we use this trick that I think is actually very meaningful to our model, which is having the party locally solve its own time lock puzzle in order to detect that certain delay has been elapsed. And this is actually something that makes a lot of sense in our real world, because we can only measure time if we invest some energy and some computation to that. I mean, if I take the batteries or if you have a mechanical watch, if I take the mechanism out of your watch and it stops doing physical work, it will not tell you how much time has elapsed. If I turn off your computer and I plug it off the internet so you cannot synchronize your time later, and I take off all of the batteries that hold your BIOS or EFI or anything together in there, when I turn your computer again, your clock will be reset, so you don't know how much time passed. In our model, we reflect exactly that. If the parties want to try to count time, they need to put in work, as in the real world. So we have the parties solve their time lock puzzles, their own time lock puzzles locally, to figure out that the broadcast delay has elapsed. And then they review their random values RI and trapdoor of I. That's the proof that that was contained in their time lock puzzles. And they wait for the other parties to do the same. If some parties have not broadcast their time lock puzzles, and we know they have not because we know that the broadcast delay has elapsed, we ignore anything we receive from them from this point on. Now, if one of the parties who did broadcast their time lock puzzle correctly and that so that it was received by everyone, does not agree with opening its time lock puzzle, if it's an adversary and it tries to abort, what we do is that all of the honest parties solve the time lock puzzle from these aborting parties and obtain their randomness from their time lock puzzles, according also with this proof that this was the right randomness in there. And finally, we define the final randomness we generate by the XOR of all of these random values. And we discard any random value that was in an invalid time lock puzzle. So here, even if you abort, you cannot bias this beacon because your message in your time lock puzzle will be retrieved. If you take too long to send your message, it will be detected and it will be ignored no matter what, no matter you abort or not. And if you send an invalid time lock puzzle, it is simply discarded. So you don't get the choice to, remember, the time lock puzzle is something that is non-interactively solved. So you cannot choose to make it look valid or invalid after the fact, after you broadcast it. Now, the interesting thing here that relates to the rundown scenario is that we can force these parties using a smart contract or a cryptocurrency platform to make security deposits before they start the protocol, and they lose the security deposit if they do not open their time lock puzzles. And what we do is that we give the security deposit to the parties, the honest parties, who now have to do the work to open the aborting party's time lock puzzle. The interesting thing here is that the adversary can abort, but it cannot cause any bias to the protocol. And on top of that, an aborting adversary will be paying the honest parties for the work that they have to do to recover from this adversarial attack. So basically, the adversary here is burning money without obtaining any advantage. Well, the only advantage it can obtain is that now, instead of completing this protocol after 2 broadcast delays, we will be completing it after 3 broadcast delays. It basically makes our protocol take 1 broadcast delay longer than it would in the optimistic case. So we have this optimistic execution, which would go through only steps 1 and 2, and then XORing all the randomnesses, which are extremely efficient because, as you have seen in the construction, computing the time lock puzzle is very easy, and checking the public verifiability algorithm for a solution is very easy. So it would be very efficient in the optimistic case. And in case that someone tries to abort, you still can recover quite efficiently just by having different honest parties solve the time lock puzzles. But even though you do the extra work, you are paid to do it. So you get your money back from the extra work you had to invest, and the adversary gets no advantage in actually having inputs and bias there. Even though I have shown this very informal, simplified description here, we need very precise and very exact statements about the delay for solving a time lock puzzle and the communication delay in order to prove security of this protocol. And it's not just a technical detail, because not just a theoretical detail, because imagine if you're running this protocol and you set your time lock puzzle delay lower than the broadcast delay, than the communication delay. Then the adversary can bias, right? Because then the adversary can actually open its time lock, it can start opening honest parties' time lock puzzles and deciding what to put into its own time lock puzzle, and then the adversary still has time to send it without being detected as an abort. So this is not just theory, this is not just technicalities. You must make a very precise analysis of the time lock puzzle delay versus the communication delay. The nice thing about doing this in our abstract composable time is that you don't really have to care when you're proving security about the concrete values of these delays. You just need to prove that there exists a finite communication delay, and that you choose your time lock puzzle delay higher than this communication delay. Then when you go to the engineering phase of such a protocol, you try to, then you need to estimate how those parameters work in the real world. But you know that if you have estimated your worst case scenario communication delay to be T, then you're gonna choose the big T for the time lock puzzle larger than your worst case communication delay. One big caveat of using this kind of randomness beacons is that nobody really knows anything about the real world parameters for these time lock puzzles. There's still a lot of work to be done to figure out exactly how much physical time it takes to do these iterated squarings and so on. So as I'm going to present in this seminar series next week, we have much safer ways to do this using guaranteed output delivery coin tossing based on secret sharing, and we can do it quite efficiently with this new construction I'll present next week. Now, given the state of affairs now, some future works coming very soon from us are AUC treatment of verifiable delay functions. So you can actually use it to build more complex protocols. As I have told you before, if you don't have composability guarantees, you cannot use these things, these primitives, in more complex protocols. You would need to totally reprove that they are not going to fail when you compose them in the complex protocols. We are also looking into a generic compiler to compile protocols for generic functionalities into protocols for the same functionalities that achieve output independent abort. We're also looking into homomorphic versions of these universally composable time lock puzzles and verifiable delay functions. And we're looking into finally doing a proper analysis of this concept of time locked transactions in cryptocurrencies and of lower bounds for block generation time, so that we can meaningfully talk about things such as state channels and atomic swaps and so on, knowing very precisely that we have lower bounds for the delay in certain transaction being executed or not. That was it. If you're interested in learning more about our work, I would direct you to the ISTR print archive, where we already have our latest version of TARDIS uploaded, and the craft paper will be coming up the next time ePrint is updated. We have already uploaded that, and what I have presented here is basically a combination of the results in both of these papers. So thank you very much, and I'll be happy to take any questions you might have now.
And since we are coming up on the hour, if you have to leave at 11, or well, on the hour, whatever that is where you are, please get your questions in first. If you can stay a little bit past, maybe hold on to your questions. Okay, open season on questions now. Nicola, I saw a hand.
Yeah, okay, hi. Thanks for the talk, it was very nice. Just a quick question on the, let's say, practical instantiation of this. What do you expect as a broadcast channel? Do you expect like using a smart contract? Because like, how do you account for if an attacker sends, reveals his TD, so his trapdoor before to some parties and not the trapdoors to after the final tick, where he's supposed to be considered a bad player and will have to pay? Like, does he have to reveal what happens if you reveal the trapdoor to only some subset of parties and not the rest? Like, how do you account for the consensus or the, like a consistent view on what is, if he has revealed or not his trapdoor?
So we, in the paper, actually have precise definitions of a delayed broadcast channel where the adversary can schedule delivery of messages. And we have also a definition of a public ledger that would be a blockchain style public ledger within our abstract composable time. And then there we are showing, we show within these definitions that when a message is sent correctly, if you follow the protocol and you send a message, all of the honest parties will achieve consensus that this message has been received before the delay. And if you don't, they also achieve consensus that it has not been received. For the case of the randomness beacon, we can do it with a semi-synchronous channel where we don't know what the delay in the channel is. But for the MPC case, that's the more complicated one, then we actually show that we need a synchronous broadcast channel exactly because of the problem you mentioned, that we need to make sure that, let's say if you have a smart contract in the middle or something like that, we need to make sure that everyone knows whether something was sent in time or not. And for that, for the dishonest majority case, for the generic general purpose MPC, we do need synchronicity throughout in our current proofs. This can be overcome, we think, but with more cumbersome consensus techniques. For the fair coin tossing, for the randomness beacon, because we have just this basically two messages, right? Registering your puzzle and then opening your puzzle, we can play with the exact delay. We don't set the delay just for communication delay +1. It's more like twice the TLP delay equal basically twice the communication delay, so that we know that all of the honest parties who do send it even if they are not perfectly synchronized, but they do send it around the same time, we can account for this desynchronization. We can show that everyone who acts honestly will have their TLPs received in time, and so that everyone else agrees that things were sent in time. For MPC, things are much more complicated because we use more rounds, and the protocols are much more complicated than just sending one TLP with a random the random string inside. But that's a very good question. For the exact details, you can check in TARDIS. We have the two-party case. The multi-party case will be in Craft. It's going to be online as soon as ePrint is updated. We submitted it this week, but still updating the next batch.
Thanks.
Any other questions? All right, I'm going to go ahead and stop the recording. And if you heard, we will have Bernardo back 1 week from today, I believe, at the same time to talk about the Albatross randomness beacon. If you are watching the recording and you don't have the information on how to join, but you would like to, please send me an email. You can use research@protocol.ai to do that. And for those of you here, I hope that you will join.